Okay, we have a full population of returns, okay, and we pick a sample of this population. So we pick two samples within this population. So we have sample A1, which are the n first returns, and we have sample A2, which are the n following returns within this population. So we cannot observe the full the entire population, but we can pick small samples within this population, which we can manage and study. Statistical analysis is a set of tools that have been developed in order to infer characteristics of the full population using manageable samples of this population. So whenever we pick a sample of observations within the full population A, each time we compute an average return of these samples, we may obtain a different value. So the average return in sample A1 may be different from the average return obtained from sample A2. So the average return is a random variable. So the sample average here is a random variable, okay, and it has statistical properties. So it has an expected value, it has a variance, okay, and we can compute confidence interval, and we can make statistical inference from with respect to the sample average, okay. So we can, given the properties of the average return, we can infer, what could be the characteristics of the next average we will compute from a new sample we would create. So when expressing the sample average as a random variable, we will represent it by capital R over line. Okay, capital R over line, that's the average of a sample expressed as a random variable. First, note that the operator expectation is a linear function. So the sum of probability of everything times the value that could take place, that could be realized with this probability, is a linear function, which means expected value of a constant times a random variable is equal to the a times the expected value of this random variable. So the expected value of a sample average from A, okay, of a sample average, the expected value of the average of a sample taken from A is equal to, so here the small r I've put a tilde on top of each small r to express the fact that these are random values, okay, because taken from a different sample, you have a different small r. So the expected value of a sample average, okay, coming from the population A is equal to the expected value of 1 over n times the sum of all the individual observations in the sample. So 1 over n can be taken out of the operator, and the operator is a linear function, so it's the sum of each individual expectation. So it's the sum of each individual expected value of r. So it's 1 over n times expected value of r, which is the expected value of the return. So the expected sample average, each time we study a sample of the population A, the expected average that this sample will produce should be equal to the expected value of the return of the full population. So a sample is a good representation of the entire population. Now, the random variable value of one element randomly picked in A has a variance, and this variance is given by sigma squared. Okay, it's represented by sigma squared, or we could call it the variance of R, capital R. It's the expected value of R minus expected value of R to the power 2. Note that the operator variance is such that the variance of a constant times R is equal to A squared times the variance of R. Why? Because it's the linear operator E times something to the power 2. So if that thing inside is multiplied by a constant, so when we take the constant out of the operator, well, this constant has to be put to the power 2. Must have the power 2. So when forming a sample of size n smaller than capital N, the full population, by randomly picking n items in A, the values of the elements in the sample are independent. Okay, so I just closed my eyes. I picked 9 elements in A. Okay, so I didn't pick them all to the left, or all the returns in 1930s, or all the returns in the 1980s. Okay, so or all the returns of mining companies. So I just closed my eyes and randomly selected n returns. So these n returns are all independent. So the sum of the variance of the sum of independent returns is equal to the sum of the variance of all these independent returns. So the variance of the sample mean taken as a random variable is equal to the variance of 1 over n times the sum of all the individual returns in the sample. It's 1, so 1 over n is a constant. So we use this property here. So to take 1 over n out of the variance operator gives us 1 over n squared times the sum of all the individual variances. And we don't compute covariance because all these returns are independent from one another. 1 over n times the sum of the variance, so 1 over n squared times n times the variance of each single element. It's the variance of R divided by n. So the variance of the sample mean is equal to the variance of each individual observations divided by the size of the sample. Of course, as I increase n, as small n gets closer and closer to capital N, there's no variance. Okay, so the sample mean is equal to the population mean. Okay, so the population mean is the sum of all observations in the population divided by capital N. If the size of my population is 1,000, and each sample has a size of 100, so each time I pick 100 elements in my population containing 1,000 observations, well, I may obtain a different average. If I increase the size of my sample to 500, then I should be closer to the full population average. If my population size is 990, so if I take like the 990, I mean, most of my observations will be the same. So my average that I will calculate with my 990 observations should be always very, very close to the full, to the average of the full population of 1,000 individuals. And if I take n, if small n is capital N, if I take the full population, there's no variance. So if n is super large, I cannot compute the average of the full population. I just cannot. It's impossible. But I can always use bigger and bigger samples. So of course, the bigger my sample, the smaller the variance of the average return I calculate from the sample. So the variance of The variance of the sample mean is equal to the true variance divided by n, which means that the standard deviation of the sample mean is equal to the true standard deviation divided by the square root of n. So SD stands for standard deviation. So if we do not know the true variance, sigma squared, of the population A, then we must use the sample variance as an estimate of the true variance, which means that the sample variance of the sample mean is equal to the sample variance of one observation divided by n, which means that the sample standard deviation of the sample mean is the sample standard deviation for one observation divided by the square root of n. This term here, standard deviation divided by the square root of n, is often referred to as the standard error. So standard deviation is for one observation. The standard error is for the sample mean. It's the standard deviation of the sample mean. So the standard deviation of the sample mean is referred to as the standard error. And with the standard error, we can make a statistical inference. So we can construct a confidence interval Y, because the central limit theorem is a theorem that states that your sample average, whatever the true distribution of return is within a population, whether the true distribution is normal, chi-square, student, whatever, name it, beta, whenever you compute averages, the distribution of the average should be very close to a normal distribution. So the bigger the sample size, the closer the distribution of the sample mean is to a normal distribution, which means it's symmetric to the left and to the right of the mean. Okay, and it has a variance, and with the variance and the expected and the mean, you can construct the probability distribution. So the central limit theorem tells us that 95% of the time, whenever you compute a sample mean from a sample of the true population, 95% of the time, your sample mean should lie within this interval here. Okay, so the sample mean plus or minus 2 times the standard error. Okay, as long as n is sufficiently large. What does it mean? So you have historical observations. Okay, and from these historical observations, you compute a sample average. Okay, so this sample average is R over line. Well, this sample average plus or minus 2 times the standard deviation of the sample mean, plus 2 times plus or minus 2 times the standard error, is a 95% confidence interval for the next sample mean you will calculate from a sample of size n. So you are 95% confident that the next time you create a sample of n observations, so this the value of the sample mean will be comprised between R, your last sample mean, plus or minus 2 times its standard error.